Hello students, welcome to EPG Pathshala. I am Professor P03 from the University of Jammu. Today we are going to discuss about a module entitled Motion of Dislocations and Dislocation Density under the paper Crystallography and Crystal Growth. The learning objectives are: we shall learn about the role of dislocations in influencing the mechanical property of crystals. On application of uniform shear stress along the Burger's vector at a crystal, the dislocation line experiences force such that the slipped area tends to grow. The force per unit length on the dislocation is given by F equal to tau B, where B is the Burger's vector. The dislocation line sweeping across a slip plane leads to displacement of crystal planes. Large number of dislocation sweeping across several slip planes is explained to be responsible for appreciable plastic deformation in crystals. Concept of dislocation density is given. The slip process resulting from a moving edge dislocation leading to displacement of a part of the crystal and deform it is explained through schematic diagrams. The slip process resulting from a moving edge dislocation leading to displacement of a part of the crystal and deform it is explained through schematic diagrams. Positive and negative edge dislocations are explained. How mechanical properties of crystals, including elastic moduli, slip, and plastic deformation, hardening by alloys and heat treatment, annealing properties, and work hardening can be explained in terms of the motion of dislocations and interactions of dislocations with one another and with impurity atoms. How to estimate the strain energy of edge and screw dislocations is discussed. One learns that the strain energy of screw dislocation is about 2/3 of that of an edge dislocation. Now we shall take up slip, motion of dislocations, and dislocation density. Suppose a uniform shear stress tau is applied to the crystal along the direction of the Burger's vector. It is shown that this leads to a force on the dislocation line such that the slipped area tends to grow. The force per unit length on the dislocation is F equal to tau B, where B is Burger's vector. This force lies in the slip plane, is perpendicular to the dislocation line all along its length and is directed towards the unslipped part of the plane. A single dislocation line sweeping across a slip plane results into a displacement of the order of a few angstroms. It means that any appreciable plastic deformation should be due to large number of dislocations sweeping across many slip planes. Clearly, the rate of plastic flow would depend on the rate at which dislocation lines sweep through the slip planes. In this regard, an important concept of dislocation density is introduced. It is defined as rho equal to S by V, where S stands for the total length of the dislocation lines and V is the volume of the crystal. It may be noted that rho has the dimensions of length raised to -2. So the quantity rho equal to S by V has the dimensions of inverse area and is called the density of dislocations. Suppose we take simple distribution of dislocations in which the dislocation lines are all straight and parallel, extend from one side of the crystal to the other. In that case, the number of dislocations intersected by a plane of unit area normal to them is the density of dislocations. Techniques for the direct observation of dislocations and determination of dislocation density will be dealt with later in the relevant section. The slip process resulting from a moving edge dislocation results into displacement of a part of the crystal and deform it. The mechanism behind the mobility of dislocation is shown in a schematic diagram of figure 17.1. The motion of an edge dislocation through a crystal may be taken as being analogous to the situation in which a wrinkle passes across a rug. The wrinkle is able to move easily than the whole rug, but the passage of the rug or a wrinkle across the rug results into the same displacement as sliding over the whole rug on the floor. If atoms on one side of the slip plane are moved with respect to those on the other side, atoms at the slip plane will experience repulsive forces from some neighbors and attractive forces from others across the slip plane. These forces cancel to a first approximation. The external stress required to move a dislocation has been calculated and it's quite small, probably below 10 raised to the power 3 dynes per square centimeter, provided that the bonding forces in the crystal are not highly directional. Thus, dislocation may make a crystal plastic. Passage of a dislocation through a crystal is equivalent to a displacement of a part of the crystal. This is how the crystals would deform if the dislocation were to move across the slip plane, and hence explains the connection between dislocations and plastic deformation. When an edge dislocation moves from one lattice side to another on the slip plane, the atoms in the core move slowly and the extra half plane of atoms at one lattice position gets connected to a plane of atoms below the slip plane, and the nearby plane of atoms becomes the new extra plane. The process repeats itself till the upper half of the crystal block completes the slip or glide by Burger's vector B. Climb of a dislocation corresponds to its motion up or down from the slip plane. Edge dislocation, for which the extra half plane lies above the slip plane, is referred to as positive, whereas the one for which the extra half plane is below the slip plane is called as negative edge dislocation. In figure 17.1, we have taken up the slip process resulting from a positive dislocation moving to the right. The result can also be achieved by motion of a negative edge dislocation of the same strength to the left. Motion of dislocation is possible either by a climb or by a slip or by a glide. Most of the mechanical properties of crystals, including elastic moduli, slip and plastic deformation, hardening by alloying and heat treatment, annealing properties, and work hardening, can be explained in terms of the motion of dislocations and the interaction of dislocations with one another and with impurity atoms. Any detailed discussion on this topic is beyond the scope of this lecture. Anybody interested to have further details is advised to refer the books entitled Dislocations in Crystals, published by McGraw-Hill, New York in 1953, and authored by W.T. Reed, and Dislocations and Plastic Flow in Crystals, published in New York, Oxford in 1953. Coming back to figure 17.1, regarding deformation of a crystal due to motion of dislocations on application of stress. When a dislocation of strung B sweeps over an entire slip plane, the two half crystals which meet on the plane become displaced relative to each other by the amount B in the direction of slip. The energy of a dislocation, be it of edge or screw dislocation, can be estimated by assuming that the crystal behaves as an elastic solid during the process of creation of the dislocation. We start considering a perfect crystal. Then let a cut be made in an appropriate way, depending on whether a screw or edge dislocation is to be dealt with, and let the two sides of the cut be displaced with respect to each other by the distance b in the manner as required. In order to create displacement, a distribution of forces is required to be exerted over the surface of the cut, and the work done by the forces in making the displacement b is equal to the energy of the dislocation E subscript d. E subscript d is equal to the integration of F dot B dA, which is put as equation 17.1. The integral is evaluated over the area of the surface of the cut. The force F is the average force per unit area at a point on the surface during the displacement. Use of the average value is justified because the force at a point builds up linearly from zero to a maximum value as the displacement is carried out. Hooke's law suggests that the density of strain energy U in an elastic body is one half of the product of stress and strain. It is usually easier to find the strain energy by considering the fact that this strain energy originates from the work done on the body by the applied forces that cause the strained condition. We proceed by considering the process of forming dislocation. This is done by taking it stepwise as follows. Step 1. We cut into the body to the line of the intended dislocation. Step 2. Next, we apply forces to the faces of the cut starting from zero and increasing it gradually until the dislocation is formed. As the dislocation forms, the faces slide past each other and the forces on them do work. The energy enters the body and becomes the strain energy of the dislocation. Let the surface forces acting when the deformation is complete be capital F per unit area. The force is a function of position on the surface capital A of the body. The work done and hence the strain energy is then given by 1/2 of summation force cross displacement is equal to 1/2 integral F dot B dot dA. This will be put as equation 17.2. where B is the displacement at the surface capital A. The factor 1/2 is taken because the surface forces build up from 0 to their final values as the displacement takes place. Therefore, the average force is taken and used here. Next, we define the core of dislocations. It is a region in the range of few lattice constants of the center of dislocation, and it is actually this region where the regular atomic arrangement of the crystal is severely affected. It is this region where maximum breakdown in the orderly arrangement of atoms is noticed. Assuming an elastic isotropic medium, it becomes easier to calculate the strain field of a screw dislocation. For this, let us consider a thin cylindrical shell of some material with radius r and length L around a screw dislocation in the z direction as is shown in figure 17.2. For a screw dislocation, the Berger vector or the slip vector B is parallel to the line of the dislocation. Here the screw dislocation is in the z direction. The elastic strain in the material at R corresponding to a displacement B in the direction of z is assumed to be uniformly distributed over entire circumference 2 pi r. No strain occurs in the r or phi directions. The strain in the z direction is of pure shear type and is given by epsilon phi z equal to b upon twice pi r, given as equation 17.3. The corresponding shear stress on the phi face in the z direction is tau phi z equal to g into epsilon phi z equal to g into b upon 2 pi r, which is given as equation 17.4, where capital G represents shear modulus or modulus of rigidity of the concerned material. The elastic strain energy is evaluated by taking sum of contributions from cylinders beginning at the core, Rho equal to 10 raised power minus 7 centimeter, and extending out to R1 of the order of the dimensions of the crystal, say 1 centimeter. Here R1 and Rho are taken as appropriate upper and lower limits for the variable r. A reasonable value of Rho is comparable to the magnitude B of the Berger's vector or equal to 1 or 2 lattice constants. The value of R1 cannot exceed the dimensions of the crystal. Thus, the average force is half the final value when the displacement is B, that is, F equal to average tau phi z equal to 1 over 2 tau phi z, here as equation 17.5. Capital F equal to G dot B upon 4 pi r, which is given as equation 17.6. From equation 17.1, we know E subscript d is equal to integral of f dot b dA. From equation 17.1, we know Ed is equal to integral of f b dA. Substituting for f from equation 17.6 in this equation, we obtain Ed equal to integral gb square upon 4 pi r into dA. But dA is equal to dz into dr. For a screw dislocation of length L, ED screw is equal to integral from t almost 0 to r1 1 by 2 epsilon phi z tau phi z twice pi RL into dr. Using equations 17.3, 17.4 and 17.5, we get ED corresponding to screw dislocation is equal to integral R tending almost 0 R to R1 1 over 2 B by twice pi R into GB upon twice pi R into twice pi R L into dr, which is equal to integral r approximately 0 to r1 gb square upon 4 pi r into L dr, which is approximately equal to gb square L upon 4 pi integral of r approximately 0 to r1 dr by r, which is approximately equal to gb square L upon 4 pi log of r1 upon r0 and indicated here as equation 17.7. The total elastic energy per unit length of a screw dislocation is therefore given by AD corresponding to screw dislocation is equal to GB square upon 4 pi log of R1 upon R0, which is indicated here as equation 17.8, where R1 and R0 are the upper and lower limits of R. If B is one lattice spacing approximately equal to 2 cross 10 raised to minus 8 centimeter, ED is of the order of 7 electron volt per atom length of the dislocation. Stress field of an edge dislocation. Let us consider dislocation of figure 17.3 in an elastically isotropic body. Dislocation is made by an operation in which a cut is made along part of slip plane, then displacing the sides of this cut rigidly past each other. The discontinuity of the diagram is shown in figure 17.3, represents a positive edge dislocation along the z-axis with a Burger's vector B along the x-axis. The stresses to be determined are 1. Sigma RR and sigma phi phi. The normal stress along the radial, that is radial tensile stress, that is compression or tension along the radius R, and circumferential, that is circumferential tensile stress, that is compression or tension acting in a plane perpendicular to R directions. And second, tau R phi is equal to tau phi R, the shear stress acting in a radial direction. For an isotropic elastic continuum, the general equation for tau R phi equal to tau phi R is equal to GB upon 2s pi r into 1 minus nu cos phi. For an edge dislocation, cos phi is equal to 1 for a cut along the slip plane. In an isotropic elastic continuum, the radial tensile stress, that is compression or tension along the radius r, sigma rr, and the circumferential tensile stress, that is compression or tension acting in a plane perpendicular to r, that is sigma phi phi, are found to be proportional to sine phi by r because of the requirement of a function which varies as 1 by r and which changes sign when gamma changes sign. However, tau r phi is found to be proportional to cos phi by r considering the plane gamma equal to 0. Without going into the rigorous and finer details of calculations which fall outside the scope of the subject here, the stress field of the edge dislocation in terms of r and phi are given by the following expressions. sigma RR equal to sigma phi is equal to GB upon twice pi into 1 minus nu into sine phi by R, and tau R phi is equal to tau phi R is equal to GB upon twice pi into 1 minus nu cos phi upon R. Here, the positive values of sigma refer to tension and negative values of sigma refer to compression. Sigma phi is a compression or tension acting in a plane perpendicular to R. The shear stress tau R phi acts in a radial direction. Capital G stands for shear modulus or modulus of rigidity, and nu stands for Poisson's ratio. Above the slip plane, sigma RR is negative and hence compression, whereas below the slip plane it corresponds to tension. It is observed that the stress fall off as 1 by R from the dislocation and becomes zero at infinity. The stress function is thus appropriate for a dislocation in a cylinder of infinite outer radius with an outer boundary free from external forces. It may be emphasized that the stresses become infinite for R equal to 0, and hence a small cylindrical region of R0 around the dislocation is excluded. In an actual crystal, this difficulty does not arise, since the material consists of atoms and is not a continuum. On the other hand, the stresses in the immediate vicinity of an actual dislocation will also be large, and Hooke's law is not valid in that region. For example, if we put R equal to B, the strains are of the order of d upon g by is approximately equal to 1 upon 2 pi into 1 minus nu is approximately equal to 1 by 4 is approximately the 25%, and so are too large to be dealt with accurately by the theory of elasticity. The energy of unit length of edge dislocation is calculated by taking tau equal to tau phi r. Capital F is equal to average of tau phi r, or equal to 1 over 2 tau phi r, which is equal to 1 over 2 integral between the limits r0 and r1 tau phi r dot bdr, equal to 1 over 2 integral within the limits r0 r1 gb square upon twice pi r into 1 minus nu dr, which comes out to be equal to gb square 4 pi into 1 minus nu integral between the limits r0 and r1 dr by r, which comes out to be equal to gb square upon 4 pi into 1 minus nu into log r1 minus log ro. This is an expression for strain energy of a unit length of edge dislocation. This shows that strain energy per unit length, that is ED corresponding to edge of a dislocation in a cylinder of infinite outer radius, that is for a crystal of infinite size, is infinite. For a single slip dislocation in a crystal, we may take the values R1 equal to 1 centimeter. That is, crystals of ordinary size, say 1 centimeter on an edge, R0 is equal to 10 raised power minus 7 centimeter. Log to the base E R1 upon R0 is approximately equal to 16. Taking G equal to 4 into 10 raised power 11 dynes per square centimeter, B equal to 2.5 into 10 raised power minus 8 centimeter, nu equal to 0.34, which are applicable to copper, the strain energy of an edge dislocation is about 5 into 10 raised power minus 4 erg per centimeter, or approximately 8 electron volt for each atom plane threaded by the dislocation line. For screw dislocations, the strain energy is about two-thirds of this value. Now let us summarize what we have learned. In this module, we have discussed slip, motion of dislocation, and dislocation density. It is explained that the plastic deformation in crystals can be due to large number of dislocations sweeping across the slip planes. On application of stress, the dislocation experiences force per unit length, which is given by F equal to tau B. The concept of dislocation density is also given, and it is explained that it has the dimensions of universe area. The connection between dislocation and plastic deformation in crystals is discussed. The concept of positive and negative edge dislocations is given. Evaluation of strain energy of edge and screw dislocations is discussed. It is explained that for screw dislocations, the strain energy is about two-thirds of the value for edge dislocations. Thank you.